All right, so here we're looking at lumber volume. So the lumber industry is interested in calculating the volume of wood in a tree trunk. So the volume of wood contained in the trunk of a certain fir tree has been modeled as, now we've got this equation given to us already. So that means when we get to step 2, we just have to write our equation down. We don't have to do anything because that's what it is. Now, D is the diameter in feet of the tree and measured 5 feet above the ground, and H is the height of the tree in feet. Okay. Now, I'm seeing there's going to be an issue here already because when we're taking derivatives, when we get to the derivative of d, we'll end up with little d over dt. That looks funny. So I would suggest maybe changing that to a capital D or to some other letter, and that way it's going to make a little more sense. Because if you're putting little d's, are we talking about this little d or are we talking about the derivative little d? And so that's going to cause some issues, I think. And so I consider using the big D good enough. I've seen other places, they say, well, let's totally change the letter to maybe a B or something else. But I think if we convert it to a capital D, we'll be okay there. All right, so it says if the height of the tree is 32 feet, so that's our height, and its diameter is 10 inches, well, remember, diameter is in feet, so we need to convert that to inches when we get to that point. How quickly is the volume of the wood changing when the tree's height is increasing by half a foot per year, assuming the tree's diameter remains constant? So here, diameter is a constant. Now this one says if the tree's diameter is 12 inches, which we need to convert to feet, and its height is 34 feet, how quickly is the volume of the wood changing when the tree's diameter is increasing by 2 inches per year? Again, we'll have to convert that to feet. Now here we assume the height remains constant. So we're going to have two things we're going to have to do here. We're going to have to do the derivative and everything with respect to the diameter remaining constant, and the other one with the height remaining constant. And so it's going to be with respect to the other one we actually take that derivative. So let's do these. So let's do step 1. And again, if you do this always the same way every time, then you're not going to have much confusion, or hopefully not as much. And so we need our dependent variables. And what are they? Well, they're D and H. And so again, I'm going to call that D, and that's going to be in feet. And then I'll have H, which is also in feet. But we also have this other one. We have volume, and volume is in what? Well, that's going to be in feet cubed. Okay. Now our independent variable, and again, that's going to be in time, and this is going to be in years because it's going 2 inches per year or half a foot per year. So we'll have that as years. So step 2, we can still get on this page. We write the equation down. And now what I'm going to do is I'm going to write it with respect to my new conversion. So it's going to be 0.002198 capital D 1.739925, and then H to the 1.133187, and that's feet cubed. Okay. All right, so now what do we do? Well, now step 3 is we're going to take the derivatives. And the first one is we want to find changing when the tree's height's increasing by that. So we're going to actually take the derivative with respect to h on the right side. And of course, on the left, it's dv. So it's going to be d dt of v, and that's going to be d dt. And now this is going to be with respect to our h, but we still have to write all that down inside. So 0.002198 d 1.739925. All right, so now we go to the next page, and hopefully we can get all this on the next page. And so we'll have, it looks like dv dt, and that was equal to, now we have that 0.002198. Now this time the constant was d, so it's just still d to the 1.739925. Now we have a number, so when we take it with respect to h, we bring our power down, so that's 1.133187. And then that's going to be 8 h to the, now we subtract 1, and so that's going to be 0.133187. And this is going to be dH dt. Okay. So that would be our actual function. We could, of course, multiply here and say, okay, well, let's take and figure out what this times this is, and we can have that, but that's going to be a lot of decimal places. So let's just leave it like that. So when we type it in our calculator, it's just as easy to type that as it is however many decimal places you'd get with that. So that was step 3. And so, uh, yeah, so that was step 2. This is, we didn't write it down. Well, go back. I want to write. Step 3 is the derivatives. So now we're on step 4, plugging in for what we know and what we need to solve for. So I think we're solving for the unknown. Now, what does it say? It tells us h is 32, d is 10 inches, and it's increasing by half a foot per year. So let's write all that down. So h is equal to 32 feet. The diameter, d, is equal to 10 inches. Well, that's equal to what? Well, that's equal to, if we change it to feet, we're going to say 10 inches over 1. And then we can say, okay, well, that's going to be 12 inches is 1 foot. So 10 over 12. So that's going to be 5 over 6 feet. So 5/6 of a foot. Okay. And then what else did we know? Oh, we knew the change in height is changing by half a foot per year. So 0.5 feet per year. Okay, so we know all of those. So let's plug them into that equation and solve for a change in volume with respect to time. Okay, so we have, all right, all this again. And D is 5/6 to the 1.739. 1.137. And then this is H32, and that's to the 0.133187, and then times the rate here, which is 0.5. Okay. Now I know that this, we have to remember to put that whole thing in parentheses. We just can't say this times 5 divided by 6 to that power. We have to be sure to put parentheses here. And so maybe we should write this one out in our calculator to kind of show that. All right, so now we need to plug this in. So that's going to be our 0.002198, and then times our, now remember, 5 divided by 6, and then raised to the power. And then we had the 1.739925 arrow down, and then times, and now might as well put it in parentheses, and then that's going to be to the power point 133187, and then we have to put our times 1.133187, and so this should give us the value now. Oh yeah, then I forgot to times 1/2, then times 1/2. And so that is our change in volume with respect to time given all those variables. So I forgot to take it times our derivative there. And so that was the piece I forgot to add on there. And so this gives us 0.0014 feet cubed per year. So that's the change in volume with respect to time. So that is a key value they wanted. Now, oops, the other key value is now we have to take and do the derivative with respect to the diameter. And so the height now is a constant. And so basically, we're going to do the same thing starting here, but we're going to take it with respect to D instead of with respect to H. And so we're going to start with step 3 again. And so dv dt is equal to, now if we just kind of skip, I don't have to write, I guess we can not skip, let's go ahead and do it all. I was going to say we could skip some steps, but let's go ahead and write it so we don't forget something. So we have d dt of v is equal to, now we have our d dt of our 0.002198 d to the 1.7399925 h to the 1.133187. And so now when we take this one, we get dv dt is equal to, now this still is there, 0.002198. Now this is going to be 1.739925 times d to the 0.739925 times h to the 1.133187. And then we have our d dt. So that's why I didn't want a little d here, because then you're going to try to figure out what that is. So I changed it to a capital D, and that makes it a little better. And now, so that's step 3. So now step 4, we have to see what they tell us our values are. Okay, the diameter is 12 inches. Well, 12 inches is a foot. So the diameter is 12 inches, which is 1 foot. So we got that. Height's 34 feet now. And dd dt is equal to what? Diameter is increasing by 2 inches per year. All right, so 2 inches per year. And if we go ahead and say, okay, well, 12 inches per 1 foot, that's going to be 1/6 of a foot per year. Okay. So now we can plug it into that equation again, just kind of like we did before. Now dv dt is equal to 0.002198 times, and now it's 1.739925 times d, which is 1, to the 0.739925, and then times h, which was 34, to the 1.133187. Now times, and we have our 1/6. Okay, so now if we plug all that in, again doing like we did last time, now we have the 0.002198 times 1.739925, and then times 1 to the, and that was 0.739925, arrow down, and we know what that is, but we went ahead and put it in there. And then times 34 to the, now that was the 1.133187, and arrow down again, and then times our 1 divided by 6, and we get 0.0346. If we, how many decimals did we go? So let's 346. So this is equal to 0.034. Let's go 7, and this is cubic feet per year again. Okay, so that is the second part. So that's part B, and this was part A. Okay, and I believe that's how they labeled it. A and B, yep. All right, so that's how much the change in volume when the tree's diameter is increasing by that much per year. Okay, so that's how we found that one. Again, just taking those derivatives. In this case, we had to do it twice, once with respect to height, once with respect to the diameter, and then we plugged in the changes of rates for the diameter and the height to get to those actual values we had there. All right, so let's pause and come back with another one.